ergonomist, kinesiologist, design scientist. I work in mechanical industrial engineering. I've moved over to the engineering world from a health and safety background because I think that's where the power is. And because I think getting a good, healthy workplace also requires having an effective workplace. There's no point being out of work. And companies are going out of business all the time. But it's a tricky business to try to get production or any kind of operations working in a good way and at the same time in a healthy way. And this seems to be the challenge because in health and safety, we're always focused on the relationship between operations, that box there, and the human, right? So everything you do at work has an effect for the human. It also has what we call the system effect. So the engineering world tends to focus on the system effects, the quality, the productivity, the performance, the delivery precision, the cost of the system, your scrap rates, all of this stuff is what I call system effects. But the operator effects then is what health and safety tends to focus on, right? So what if we think about the effects of work? What are the effects of work on people? Anybody? Name one thing for me. Fatigue, okay. What else? On the back table. What does work do to a person or leave a person with? Injuries, okay. Anything else? From the middle tables? We have fatigue, we have injuries, that's all you get out of work?
How about pride?
Pride? Did I hear that?
Pride.
Yeah, thank you. Yes?
Putting food on the table?
Food on the table, thank you. Yeah, other ideas? What do you get from work? Quality now is a system effect.
Enjoyment.
Enjoyment, sometimes. Some days. Yeah. Identity, competency, learning, knowledge, ability, all of these things we get from work. Sometimes we get injured, and that sucks. What I'm trying to do in my work is look at the design of the workplace in ways that foster these good things for people, but also get the job done. And we look a lot at what we call profit drivers. So yeah, everybody wants to make money, but the managers need to focus on what is it they think is going to drive their profit. And the problem is, with the current worldview of these being separate, is that we haven't really accounted for the fact that the operator is actually inside the system, right? So that it's not just an outcome, it's also an input. So if we increase competency, production is going to get better. If we increase skills, knowledge, communication ability, performance is going to go up. But if we generate injuries, if we have fatigue, right, then we're going to run into problems. And I don't care if fatigue causes injuries or not. That's a scientific question. The engineering question is, how does fatigue affect people's performance in operations? So this is my next question to the audience then. Right? If work causes fatigue, how does fatigue affect the system? I'm interested in your experiences from your workplaces. What have you seen happen due to fatigue in your work? Nobody here has fatigue in their workplace? Tell me more about that. Okay, so quality goes down. What environment are you speaking of, if I may ask?
I'm in communications background.
In communication. So in the communications work, you're fatigued, you're not responding as quickly, and the quality of your work goes down. What does that lead to?
Leads to, well, it hinders people having speaking for because I don't present my work as I should.
Okay, so the quality of presentation goes down. I know my lectures are not as good if I'm tired, right? This is what we're talking about, isn't it? Jack's better than me. Jack's better than me. I knew that from the start. Okay, other effects of fatigue? Yeah.
Waste.
Waste. Can you spell that out for me?
W-A-S-T.
You've got a wise guy. What environment are you talking about? What steel fabrication. Okay, so can you just tell me how that works?
So guys working on large steel silos, and as a result of fatigue or being overworked, they're making errors, and the error product, of course, becomes waste, so it goes into a scrap bin and gets sold.
So not only is the product not coming out right, but you're generating a whole lot of scrap materials that you also have to pay to get rid of, right? So we have these problems. Can anybody think of another scenario? Quality of work goes down. Yeah.
What about cognitive impairment, working memory, perception of tasks?
Okay, so how does that play out in your work?
If I don't perceive what I'm being provided with, then I'm not making the right decisions to effectively produce the outcome.
Okay, so your decision making starts to suffer, right? So already with these three examples, right? The quality of your performance goes down, you're making weak decisions, there's quality errors in work. We start to see that the fatigue has a negative effect on performance. That's an engineering problem. It's not necessarily a health and safety problem, and I don't care. But it's a place where we as health and safety professionals may understand why work is not working the way it should. And this then becomes a very, very interesting issue, and one that engineers are not equipped to deal with. They need your help. We need your help. Because we're not trained really to think about people adequately. Your best bet's with an industrial engineer. They'll get some ergonomics training, they'll get some human factors training, but if your operations are being run by a mechanical engineer, God help you. So this was my major point before I pass off to my colleague Linda, that these things that are creating fatigue lead to declines in work performance, declines in the workplace, problem products, and decreased performance, bad decisions. All of this stuff starts to sap your competitive ability. So I want to tell you one story of a little project we're doing with a little international electronics company based in Waterloo, whom I'm not supposed to name. We did what's called a concept mapping exercise. And we wanted to work with the engineering team, the senior managers. We wanted to understand how are they thinking about human factors and how can we tie human factors into their strategic goals. The simple idea being is that if we're seen as contributing to their strategic goals, to the things they really want to achieve, we're more likely to get our human factors built in. So we're working to change the way they design their production to include checks and controls for human factors elements. And to do this, we did this cognitive mapping exercise, where we asked each of the management team, and we had 7 or 8, each of the management team asked them, how can human factors help you reach your strategic goals? And we draw it out on a piece of paper like this. We put the strategic goal at the top. Maybe it's crushing the competitor, or maybe it's producing high quality product. And then we start to ask them, well, how are they going to reach that? And then we start to ask them, well, how can human factors start to feed this? And we draw it all out on the map as you go. It's quite fun. When we take the manager's responses, oh, this isn't reproducing so well. It's a Mac. It's okay. It's okay. We wind up with an image a little bit like this, right? And this is really kind of what Richard was just showing you. So picture Richard's slide inserted here. But what's interesting is that we talk to a number of managers and we glue their maps together. So we go to something a little bit more complicated, to something really complicated, and then we do some analysis. And we start to see that somewhere in the middle here is this concept fatigue. And we look at the number of linkages that any one concept has tells you how central the concept is. Let me try that one more time. Okay. The number of connections to a given concept. So if this box here in the middle has 16 arrows going out, to 16 different boxes. It scores 16. If each of those have 5 more arrows goes out, it scores, well, you score half for each of the secondary arrows. So it's a weighting system. Fortunately, there's software that does this for you. Okay? But what it tells you numerically is how central, how connected a core concept is. Is everybody with me? So we're trying to find out what's the core concept for these industrial engineering managers around how human factors connects to their goals. Because we want to serve their goals so that we can get our bid in at the same time. And this is what we ended up seeing. All right, so right at the top we have increased quality and improved systems design. Well, fair enough. Those are the goals. They should be the most connected. But number 2 was reducing injury and or fatigue. Fatigue came out actually stronger than injury. They weren't that interested in injury. They don't have that many injuries. But they have a lot of fatigue. And they understand it. But they don't have a way to deal with it. That's, of course, where we come in. So, of the 9 managers we talked to, 7 of them were talking about fatigue. Only 2 even mentioned injury. We're talking about fatigue. So when we start to look at fatigue here as a central concept, I don't expect you to read everything, but it just illustrates that fatigue is connected to so much of what the engineers are attending to. They understand that fatigue is a problem. They get fatigue. They don't even need a definition. So we see some comments like this. Fatigue and quality seem to go hand in hand. Fatigue is not only the root cause of our quality problems, but one of the biggest factors. These are very experienced people. Fatigue seems to sum it up, says one. This is what they got out of the whole exercise, that fatigue is a serious problem. And that opened the door, this exercise, and you can do this with your own manager as a consultant, you can do this. There's no magic to this technique, right? The software's cheap. You just need to sit down and ask them, what are you trying to achieve? And how do your people affect your ability to reach that goal? I guess we do questions at the end, do we?
Yeah.
All right. So last 2 slides before I hand off to Linda. When Richard first asked me to do this, I was preparing a classic industrial engineering course on work measurement and time studies. And I thought, oh yeah, well I can present some stuff in the chapter. It's just so damn boring. Oh my God. I'm falling asleep in front of my students. Here's 2 points though. 2 little points from industrial engineering textbook type knowledge, right? Before everybody nods off. Engineers are familiar with allowances. The concept of allowances are well developed in industrial engineering, and there's a lot of discussion in the textbooks, and you can read the chapter yourself, but get a good strong cup of coffee, right? We've got all kinds of allowances here, as you see in the top row. Right? I'm going to focus in on what's called a basic fatigue allowance and a variable fatigue allowance. Okay? 2 forms of allowances that people usually build in. The basic one is looking at the whole job and sort of saying, well, how fatiguing is this? And typically all of these allowances, when you add all this stuff up, somewhere around 14%, 15%, but it varies by industry. And that's what's added then to the so-called normal time, the average performance time that's calculated. Then you have your variable fatigue, which is an extra bit that you lay on. If, for example, you have very heavy loads coming in on a given truck, you might give that particular loading, unloading operation a bit of extra time. And these allowances are the kind of thing that engineers use to manage fatigue. The problem is, do they know how much fatigue they've got? And is that done properly? And this, I think, is where the health and safety professional and the ergonomist can really start to help. We do have some equations, this kind of thing. This is a percent rest calculation based on the energy expenditure, based on how active the job is. And when we look at this, we have kilocalories per minute, and there's software that can help you calculate that stuff. Right? These are sort of fairly standard workload calculations. Just how intense is the work, and how much rest do you need? And this function for some reason gives a curve. There's never any explanation where this stuff comes from, right? It's not like kinesiology. But you can see that, up until sort of 5 kilocalories per minute, there's no extra rest allowance required, and from there on it goes up very, very quickly to the point where, 60, 70% of your time should be spent in rest. But this is incredibly intense work. I don't think it covers, at all what's happening for people doing desk work, office jobs, white-collar work, or even a lot of modern assembly today, right? Assembling your cell phone is not heavy work, but it can be quite fatiguing for certain body parts. And this is the challenge, I think, and this is where the gap is in our research. So I hope with this segment, I've kept you awake and given you some thought around, why we may want to address fatigue, why we want to address, the human concerns in production from the perspective of engineering. There's a valuable contribution. We don't need fatigue to be related to injury in order to know that it compromises performance. And so linking to the goals of your managers, understanding what management is trying to achieve, and being seen as contributing to that is going to get you further than simply sort of walking in and saying, this might be a health and safety concern. That by connecting your goals to their goals, you can start to build a coalition and get support for early attention to this, which is where the savings are. Right? Retrofitting, going in and fixing stuff on the floor, very expensive. You want to be getting in at the design stage with this kind of rationale that we're going to have a better system, better performance, better decisions, less mistakes, less scrap. These are the things that are going to excite people about what you have to offer to the development of workplaces. So with that, I'm going to hand off to Linda.
Thank you, Patrick. So for a little while now, I'm going to give you an example of a method called the Ergo Index, which can be used to assess recovery need in manual work. And it was developed by a group of Swedish practitioners and researchers in the 80s, based on the needs from mainly the construction industry, and using literature reviews, literature sort of studies, and based on their own experiments, they derived a model, which we now have refined. But I'll give you the background first. Like Patrick was already saying, that fatigue and injury are sort of in the focus of the manager, and there is some kind of knowledge that these factors actually compromise the company's strategic goals. So, what do we know about the musculoskeletal disorders? Well, it has been proposed that there is a linkage. One of the main factors to actually get this kind of injury is an insufficient recovery. And depending on the load situation, like the loading situation with the load level and so on, the recovery need varies. So if you have something that is really demanding, you're more fatigued and you would need a longer recovery to recover and do the work again. And if you are fatigued, this, as we've already heard, also has an effect on the performance. So the group of these practitioners and researchers, they were sort of posing the question, would it be possible to try to combine an assessment, both from an ergonomic point of view, looking at the loading situation on the human, and also the production economics, somehow regarding time aspects, since time sort of influences the production. And I'd like to give you one example of different ways to analyze a working situation. In this case, we have somebody who's trying to chisel a hole in a concrete wall. On the left-hand side, he's using his body as a support. He has to lift the machine and push it towards the wall while it's sort of chiseling. And he also gets quite a number of, or quite an amount of vibrations into his body. Whereas in the right-hand side here, that example, he uses a support instead, which carries the load, and if it has a gas spring, it also reduces the vibration that the worker is actually gets to it. Sorry, I can't find the English word right now. So a traditional way to analyze this would be that, okay, let's drop this guy and see how long time he needs to do this work. And we assume that it takes as long time whether he uses a support or he uses the body as a support. So the unit time would in this case be 2.7 minutes. And then we tried to make some kind of ergonomic assessment, and we might look at biomechanics and the compression force on the spinal load. And in the first case, using body, we would derive at a compression force that's about 2,700 newtons. Whereas in the right-hand case, sort of the second where you use the support, this compression force would be reduced to about 1,000 newtons, which is fine. It looks good. But as probably many of you know, the limit value is up here at about 3,400 newtons. So it doesn't really make an impact on the decision makers that actually we should get the support for the chiseling work because the ergonomics is really improving. So it's not the best argument. And looking at economics, the manager might say that, okay, we know how many minutes it takes to chisel or make one hole. We could try to convert that to some kind of monetary measure instead, saying how many dollars, or in this case Swedish crowns, does it cost to drill a hole, using like the cost for the worker. So in the first case, using the body, we would derive at 585 Swedish crowns for one hole. Whereas if you use the support, you have to add the cost also for the support, which then adds to, instead of 585, you derive at 630. So the question I'd like to pose to you, if you were a manager and had this kind of information, would you invest in this alternative too? Hands up. How many would do that? A couple. Okay. So the rationale of Ergo Index is instead that, okay, if we look at this time, in this case, 2.7 minutes, that is the time that it takes for this construction worker to chisel a hole and then start doing the next. But if we analyze that, we see that only a small proportion, or just a fraction of it, is actual loading time, the time when he's active with the machine. The rest of the time is needed for recovery, so that he can recover from his fatigue to such an extent that he actually continues working. So in the left case, it is 2.7 minutes, but when he uses the support, he's not as fatigued, and therefore the total time, which is the sum of the chiseling time and the recovery time, is lower. So by that, trying to sort of transpose that to the economic outcome instead, we say that, okay, we still have 585 in the first case, but also when we add the cost for the support for the second case, we still arrive at a lower cost. So then the rhetorical question comes, would you, with this information, be more willing to invest in alternative two? Hands up. Okay, right. We can go home. Good. So the thought behind, and I've already said it, is that the Ergo Index model tries to evaluate jobs from both the human perspective, like an ergonomics perspective, looking at the load level and also some risk for injury, and also time aspects that sort of could be linked to production economics. And this to be able to choose between different ways to carry out sort of work tasks. And it was, as I said, based on literature and experimental studies in the 80s, and then in the 90s we started to further develop it because it had imperfections, like kids' sicknesses, as many models have. We presented this both in Sweden and Europe and also in North America in conferences. And to my surprise, I was contacted by General Motors in 2004 who said, "Oh, is this Dr. Rose? Well, we've been using your model since the 90s, but we have some questions." So actually, General Motors have been using this since the 90s to try to reduce the problems that they had in their plants in Austria, but also in the US. So also discussing with industrial partners in Sweden, we found that maybe we should try to refine them all a bit. So we just have, and we've been focusing on endurance time and resumption time modeling, repeated loading situations, and rating of perceived discomfort. And one thing that is quite rare with this method is that we base it on subjective assessment that experienced workers have been, well, we have used experienced workers in experimental setups. And we believe that if we use them as a base, they are better judged to know that since they're still on the job and haven't sort of quit because of illnesses, they might be able to judge how long time they can go on, when they need to break, and how long they need to rest before resuming a task. And that sort of assessment could be a better predictor of a recovery need that's more valid or more accurate than, for example, looking at the force regeneration capacity. So we use experienced workers in experiments to form a base for a model. So that's what we've done. Some quotes about the Ergo Index from the GM is that it's used both proactively, design, and reactively. And it's used to make determinations about recovery time in jobs, and if there is insufficient recovery time, then the job is changed. And that is, I think, the best payback that a researcher can get, that actually something you've been working with is used out there. So that's yes. And I'd like to also give you an applied example of this newly further developed method that we just finished this year. And I'm going to take an example from the construction industry with an assembly task where you try to assemble windows at the construction site. So we could either do this manually. Here in the left picture, we have two construction workers that carry this window, which has a weight of 75 kilos, to assemble it. And in the right-hand case, the same construction workers use a robot to do this task instead. So you ask them, so how is it? How do you perceive the work? And they say, well, the first case, it's heavier on the body, but it's faster. And the second case, yeah, it's easier, but it's slower. So we actually trained them on the job. But I'm going to show you how you actually can use this new Ergo Index tool to make an evaluation. And up to now, we just have a very simple Excel spreadsheet model, but we're going to develop a more user-friendly method also. But anyway, this is the input data sheet. We're asking questions about the working distance. Is it 0 to 40 centimeters, or a bit further out, or like 60 to 80 centimeters? What about the working height? Is it down here between the foot and knuckle? Is it in this region? Is it shoulder to head? Or is it above your head? And type of work, also very simple. Is it lifting, pushing, or pulling? So you sort of click the right variables there, or the right values. And then you also add the exerted force, which in this case is 375 newtons, and the loading time, which we got to 15 seconds. And we name this manual window transportation. So what comes out is kind of a blurry sheet that I'll try to explain to you. Like on the left side up here, we have information about the time needed. On the right-hand side, we have load-level information. Then in the middle, there is, if any, risk of injury statement. And on the bottom side, we have input data table and also results table. So what does this tell us then? Well, for this manual window transportation case, the Ergo Index states that first you have loading time marked in red, which was given 15 seconds. And the green on top of that is the calculated resumption time, the time needed to actually resume work. So those two together make out the total time, which is 67 seconds. If we look at the proportion, how much we actually can work in this sort of situation, we can see that you work for about 22% of the time, according to this model, whereas you need 78% to actually recover so much that you're willing and should resume work. And the load level, which is represented by a medium person, where we have combined data from a medium male and a female, shows that in this loading situation, they use actually over 80% of their maximum capacity to carry this 75 kilo window to the right place. And also, using Swedish legislation for some of it, their limit values, we found that according to that, this load level is assessed to be to a high risk of MSD problems. And then we have also the results on the table, saying setting the loading time, the total time, and the load level, and the resumption time. So that was the first part. But if we want to compare this with the other method, we'll have to use a data input sheet again. And here we're working, as you see in the picture on the right-hand side, a longer working distance, the same height, and we're pushing something, and we measured the pushing force to 80 newtons. This, though, was slower. So instead of 15 seconds, the worker used 20 seconds to complete the task. So we call this the robot window transportation. And the results look like this. Again, on the left-hand side, info about the time. On the right-hand side, info about the load level. We see that the red part of the diagram on the left side is higher because we have a longer loading time. And the calculated resumption time in this case is 39 seconds compared to 52 in the first case. So the total time adding these two together is 59 seconds. And we see that the fraction of this whole time that you actually are productive or can work is 34% instead of 22 in the first example. Looking at the load level, we see that it has decreased by about half. So it's less, or roughly about half of what it was in the first case. And there is no warning that this actually sort of exceeds the limit values in the Swedish legislation. So if we compare these two situations, we believe, or we see that this could be used then as an information to base your decision making on. What tool should we use? What system should we, what technique should we use? This could be applied to different kinds of mechanical or manual work. So we also evaluated this on the construction site, and the subjective rating by the workers said that using the Borg CR10 scale, in the first case, they rated the discomfort to be strong, like a 6 on the Borg scale, whereas in the second case, they said it's really almost nothing. And using a body map, you also see here on the right-hand side, red means like heavy load, yellow means, well, somewhat loaded. And you see that in the first case, the most part of the upper body is affected, whereas in the second case, it's really very, almost nothing. So this is a way to then evaluate or assess the workload and the time and be able to sort of choose a better or a good working technology or a method. And another way that I'd like to say that, well, if you're better informed about how the load situation and the time aspects, you make better decisions. I'd like to end with another example that sort of we got extra from these, the study of the experiments, where we looked at the perceived discomfort that the workers that were included in the study experienced every 30 seconds, both during loading and during the recovery. And this is an example then, and we were able to model their discomfort during loading, but also during the recovery process. And I'd like to give an example where you see that, let's assume that they're working at 25% of their maximum capacity level, and that the loading time is 50 seconds. Then, I'm very sorry, but this slide doesn't show the thing, so I'll have to improvise that instead, because Mac has done something to my slide. Anyway, I don't know if you can see, if everyone can see me, but what I'm doing. So in the first case, the discomfort goes up, and then you rest for 5 seconds. It starts going down exponentially, actually. Then you start again. So the discomfort level goes up linearly, and then you give the person another 5 seconds rest, so it starts declining. But just after a couple of cycles, like after 5 cycles, you're up at level of perceived discomfort at 8 out of 10, where 10 is maximum. So you clearly cannot go on with this kind of working pattern. So that affects both the worker's well-being, but also the system performance, because you have to take a break. Whereas in the second case, which you can't see either, if we instead of 5 seconds break have a 25-second pause, we see that, okay, the load level, the discomfort level still goes up in the first cycle, but given 25 seconds of pause, it declines and starts again. And we never come above 3 on the bar scale, rating discomfort. So that seems to be more like a steady state or something that's sustainable that you could go on. And that probably would lead to less production problems and also to less health issues. So this is another way that actually companies could use to play around and see what kind of, how should we trim our production system to have long enough pauses to actually make both performance and well-being happen in a good way. Okay, so let's end up. And the 5 key points. Would you like to start, Patrick?
Sure. Richard asked us to summarize into 5 key points. I think the first one that we're trying to make here is that fatigue indeed affects system performance and therefore becomes an engineering management concern, not just a health and safety concern. We've seen that engineering managers get that fatigue compromises quality. They understand the link viscerally, and but they need help actually managing it because they don't necessarily have the skills and tools to do that. The engineering managers we've worked with, they don't think about ergonomics. They don't think necessarily about safety, other than that should be a given. But they do think about fatigue, and that becomes a very interesting inroad then to get a more humanly designed system. You want to do the last 2?
All right. And also, at higher loads need higher rest allowances. And the last point we'd like to give to you, like as a key point, is that rest allowance models actually allow you to balance fatigue and productivity concerns, as given in these 2 examples. Okay. Contact info to both of us. Okay, thank you.
We have 2 minutes for questions.
That's my line. We have microphones, as I indicated, and so we have a question over here. Please state your name so we know who you are.
I'm Syed Lakfi from Occupational Health Clinics for Ontario Workers in Toronto. I have a quick comment and a question. As an ergonomics practitioner and industrial engineer, I have special interest in time standards development process because I often advise major unions on time study issues. One of the sticking point or challenge is how the fatigue or rest allowance is determined for the current job because of its direct link with injuries. I want to get your take on the current fatigue allowance development process.
It's underdeveloped.
So what sort of, I know that there's an ILO method there and so on.
Yeah. I mean, there's a range of suggestions out there. The ILO suggestions, and there's a couple of others from American groups on what fatigue allowances should be. But it's never really clear how you set those allowances. I think the kind of approach that Linda's demonstrating is very interesting in that sense that it's connected back to the physiology. The problem with time studies is that they only deal with time. And we know that fatigue is not just about time, it's also about the workload and what you're doing and a bunch of other stuff. So until we can get tools like the kind of thing Michael Grieg is working on, where we have physical load and time linked together, or the Ergo Index model, you're going to have a hard time with it.
Other questions?
I'm John Granny. I used to teach neuroanatomy at the University of Waterloo, and as well as gross and I think it was very gross. I have a question for Richard about the wonderful slide with all the arrows. I'd like to see you put a few more on it and develop the whole central nervous system part of fatigue, because I'm sure there's a feedback mechanism from fatigue to the nervous system. And if you just think not about hockey, because that's a bad way to say, but about football, and how seeing these guys running down the field and just killing themselves in order to win, to get the Grey Cup, they're going to be tired, but they're not going to feel it now. No, not until the game's over. So motivation is a big thing there, and I'd like to put in a plug for something I've always believed in, but nobody else does, it seems, and that's called profit sharing.
Yeah, profit sharing is a viable form of getting motivation if it's properly structured. I think it can also lead to overwork and injury if it's poorly managed. So you have to be very careful about how you structure reward systems for frontline employees. Absolutely, motivation is a huge one. That's another key word that managers pick up on, and nobody's really going to be super motivated by a job that's super fatiguing.
Thank you. Just again, Don, that's not my slide. Jim Potvin provided me with that one, and so I thought it was such a good one. And I had Jim's name in the corner there. Maybe I should have emphasized it a lot more. But I thought he was pretty close to a William Tell with that one. So thanks very much for that slide, Jim. Any further questions?